All right, here we go. It is physics time. So we're looking at the velocity in a river question, velocity of like a boat in a river, and going to make sense of these questions here about what the fastest possible route is to get across and what direction to aim to go straight across. And then we'll just be able to work with relative velocity situations more generally. So here we go. What was your answer here? Which way should you aim to get across as fast as possible? Well, the answer is exactly what I showed here. Okay, if you just aim straight across, then basically what you get if you aim straight across is you get your velocity in the across direction is 6, right? So you have that gives you your fastest possible velocity to get across. I'll show you more about this soon here too. But yeah, it gives you the fastest velocity in that direction. So you aim straight across the river, let the current sweep you downstream, fine. Your only goal was to get across, right? Your goal wasn't to get across to this spot right here. It was just you want to get to the other side, right? So it turns out the fastest is, to touch the wall on the other side is just to aim straight across. Okay, so you need your velocity in that direction to be as big as possible. And so if you aimed any other direction, you'd only have a component, right? If you aimed any other direction of any kind, you'd only have a component of the velocity in that direction. So it'd be smaller by definition. And yeah, so aim straight across. And you get across. You have your whole component in that direction, so you get across as fast as possible. Okay. I know that it can seem weird, and so if you're still, if you still think aiming upstream, so you travel a bit of a shorter distance, right? If you aimed upstream and to the point where you end up going straight across, certainly is a shorter path. You go across, straight across. And I suppose depending on if the question was, to get across to this exact spot, maybe that would be better. Maybe it wouldn't. I don't know. It depends on, I guess, how quickly you could run along the shore. So it'd be a different kind of question. But the way the question was is literally, I just want to get to the other side. And so this is the answer. And we can show that this is true. So if we were to look at the old situation, we aim straight across, get swept downstream. Let's just aim a little bit upstream at least, right? So we get a little bit of a shorter path and so on. And I'll show you the details. So that would give us a path across around like this, I guess, right? And so we'd have that path. And so we're going to run some numbers here. Let's just first get the component. And so we have that this angle in here, call it theta here, right? That theta is the 10 degrees. We're going to aim upstream just for instance here. So the y component of the velocity, we're looking for the y component of the velocity. You can see that the y component would be right here, right? That's the vy component. So it is adjacent to the 10 degrees, and so it'd be 6 cos 10 degrees. 6 cos 10, when you calculate it out, gives you 5.9088. Okay, I've done the calculations ahead, so it'd be a little quicker and more efficient here. Meters per second, right? And so you can tell, obviously, you have a smaller velocity, like we said, right? This is smaller than the 6. It's only a component of the 6. And so if you were to look at the velocity in the y direction, displacement in the y direction, and time, you'd have the 5.9088. You'd have the 30 that you're crossing. That was the original question for the distance across the river. And we'd have this, right? So we end up with delta t equals the 30 divided by the 5.9088. Want some steps along the way of that. Obviously, we'd multiply both sides by delta t, and then that would get rid of that part. And then if we divided after that the 5.9 out, I'm just going to say 5.9 dot, right? You'd have the 30 divided by the 5.9, and that works out to how many seconds here? That works out to 5.077 seconds. Okay. The previous version of our work, we aimed straight across and where's my work for that? I think it was earlier up, right? We had the velocity in the y direction. Oh, that's a different question. Where are we going here? So it was 5 seconds, right? We just aimed directly across. So we had the 5 seconds, okay? So you can see it's a little bit longer. We only aimed upstream a little bit. So of course, that's just what's going to happen. So it's a little bit slower. So you can tell it going at a different angle. Even though this is a shorter path that we're traveling, it takes us a little longer, okay? I'm going to go a little bit beyond or overboard here. Bear with me. I'm going to just go with a little bit more analysis and try to show some of the things that our math skills can do. So if you look at this triangle, so as an extra here, if you look at that triangle, it's not a right triangle, right? And so if we want to deal with it some more, we're going to have to deal with, use different math skills. And so let's do that just to show the power of the math that we have at our disposal. I'm just going to grab this whole thing. Right here so we can look at it a bit more. So we have this triangle set up, right? And so I'm just going to make it a bit bigger, and I'm not going to worry about using the ruler and whatnot this time. Just going to make it nice and quick here. So we've got this situation, we've got the red vector that goes a little beyond like that, and we have the green resulting like this, right? And we're not sure of some of the information here. We know this is 10. We know this is, what do we know here? We know the arrow is 6, right? We know that's 6 meters per second. And we know the red one all the way over is 3, but that doesn't, yeah, whatever. I guess that's what we have so far. So if we were to add some more information to this thing, we could put in the 90 degree that's there. Notice that if we were looking at the 10, the 90, and the unknown there, we'd be able to get that this is 80. Of course, you could show, unknown plus 10 plus 90 equals 180 and so on, but let's just go for it here. So we have that. And we do know also the distance across is 30. So we have two sets of information for this. This was the 6 and 3 was the meters per second information, right? And there's also another version of this triangle. It's based on displacement. So we have the 30 meters across as another value to do with the system. Okay, so I don't know where we want to put that. Right there is good. And so if I were to look at the distances involved on things here, I'm going to do a couple things. Let's first of all look at the velocity in this direction. Then we'll do distances afterwards because I've got the 6 and the 3. Let's go for it, right? What's that velocity? Well, if you look at the situation, you've got a non-right triangle, and we have the way I teach cosine law in math, anyways, at least, is I show if you have an opposite angle and side pairing where you have the angle or the side, whichever, and you have the other two sides, then you can use cosine law. So cosine law essentially is this, right? Kind of like the Pythagorean theorem, but then minus 2 of these two sides here, and then cosine of the angle. So review cosine law. This is a good review of cosine law, or maybe you might need to go review it some more. But so the v that we're looking for squared is equal to the 6 squared plus the 3 squared. I won't bother trying to color code everything here. Times the 6 times the 3 again, times 2, subtracted, and we have the cosine of the angle, which is the angle opposite to the v, which is the 80 degrees. Right? And so if we run the numbers here, we're going to have easy numbers here like 36 and 9, and the 2 times the 12 is the 24, cos of 80. So we end up with 45. Take away 36 times, 36 or 24. 6 times 3 is 9 times, yeah. So I thought that was 6 times 2 there. 6 times 3. And so this is 36. And so cos of 980 times the 36 is 6.2513. You can check with a calculator, all this stuff, but we get v squared is equal to the subtraction of that, which is about 38.7487 dot dot dot, whatever, right? Lots of decimals. Take the root of both sides, and we get the velocity is plus or minus, but obviously we're just going to call it the positive velocity version of this. Gives us 6.2248 meters per second. So how does that compare to what our velocity was when we originally did this? If we just go aim straight across and let the river sweep us downstream, we had a velocity of 6.7 at an angle of 26.6. Right? In this case, we just calculated out that we have a velocity of 6.228, right? So we can point out, if you aim straight across, velocity ended up being, the combined velocity ended up being 6.708 or whatever. And so this is slower. And you can certainly think of this as, you're fighting the current a little bit, right? You're fighting the current by trying to go upstream a bit. Trying to go upstream. So it makes sense that you're ending up with a slower speed. Obviously, if you aimed straight up at 6, you'd end up with a velocity of 3 upstream, right? So there's another question coming up like that as well. I'll add that one to it maybe. But we're a little bit slower because we're fighting this, right? And so this is, again, going along with the idea of leading to slower overall. So that's the velocity part of this discussion. And then if we get the distance, then we can actually do a velocity and distance and time for that diagonal and see that it agrees with our time from this situation, right? The time would actually be the 5.077 seconds, okay, based on that vertical component and the vertical displacement. So just to see that everything makes sense, everything's agreeing, or like everything's working basically, right? So let me get rid of my circled bit here, although we might end up doing the same thing in a bit, just for the displacement version of things. Let's see here. So I've got the 30 meters, right? So let's work with a purple now, just to show we're doing new stuff here, right? So the 30 meters that we have here, we're going to be able to get the number of meters there because of the right triangle, and then we can keep going. I'll show you. You can end up calculating all of this. Okay, so we'll get the red distance and the green distance basically. So in the right triangle, we've got the 10, the 80, and so on. And so if you look at the this side directly here, this one here, we're looking at cosine, right? Because we have cosine of 10 equals adjacent over the unknown here. Okay, so I'm going to call that I'm just going to call it A. Just side A, basically, of this thing. Okay, so this is A here. All right. So we're going to do cosine of 10 equals 30 over A, and purple by accident still here, but whatever. Multiplying both sides by A and dividing and so on solves to give us 30 divided by cos of 10. And so we're getting an answer of 30.462798. I was having trouble deciding where to round, basically, when I was writing it down. All right. Which makes sense, right? 30 across, if you're going on an angle, it's a little bit bigger, right? And then we can also figure out the value of, I'm going to go with a different color here just for emphasis here. We can figure out the value of this using similar triangles, right? Look at the multiple going from 6 to 3. So we had a 6 to 3 in the velocity version of things. And so we're going to have a 30.46 going to be what? Well, you can tell that the pattern, the jump going from there to there is just a divide by 2, right? So using similar triangles work. We have a divide by 2. And so dividing that by 2 gives us 15.23. A couple decimals more if you want or whatever, but this number here, this side is 15.23. And so we're going to be able to get the size or length of the green one in a very similar way. We're going to say, okay, this B side here is B squared equals all the other sides, exact same cosine law work. So I just need to put this 30.46 on here to help myself when I'm looking at the triangle. 30.46 ... and so on, because I'm in the habit of looking at the triangle and saying, okay, it's going to be the 30.46 side squared plus the 15.23 side squared minus 2 of those two sides. So 2 times the 30 times the 15, and then cosine of the angle, which that's opposite the green side we're looking for, which is the 80. So I'll color code that just to emphasize the idea that they're corresponding or opposite sides or matching sides, whatever you want to call it. Oops, that was supposed to be green. Markers were in the wrong spot on the smartboard, so it messed me up. So we have that, and then the numbers obviously work out to whatever they work out to here. So when you're squaring 927.81 and plus whatever minus whatever and so on, what we're getting in the end here is 998.69, and then that's what b squared is. Rooting both sides gives us b equals plus or minus, but we're just going to say it's a length, so ends up being 31.6. Okay, that distance was 33.5, right? So it is a shorter path overall, right? So it is shorter as expected, or as we described, right? But if we look at the velocity, so let me do this in green to emphasize it's the green stuff. Smartboard's slowing down on me here. D equals delta D over delta T. And so we have the velocity in the direction is the 6.2248 that we had, and this distance of 31.6 and the time. And when you solve that out, you end up with the 31.6 divided by the 6.2248. If you check on a calculator, you'll see that gives you the 5.0768. So it's like a math flex mic drop moment where you're like, all right, everything should be making sense here with this combined velocity that I worked hard with cosine law and whatnot to get, combines with the calculated length, again based on cosine law, and so then you can show the velocity in the vertical direction works out to, where did I do this one? Works out to the 5.077. And then when I get the velocity in the diagonal and the distance in the diagonal, it works out to the 5.077 as well, and so on. Okay. Whew. So like I said, that was a little bit of a diversion from what I'm really trying to accomplish here. But I didn't show the sine law and cosine law stuff in the past, and I just thought I'd show that it really was necessary in this case if you wanted to analyze these things. Okay. And it also relates well to something I'm going to show you soon. So I decided to go for it. And so which way should we aim to end up with the fastest possible velocity relative to the shore, right? That would just be aim like straight downstream, right? That way you'd get your velocities adding up. And then I said I'd add onto this slide here, what about if we aimed upstream? So what if we aimed upstream? So let's aim 6 up and the 3 down. And it's pretty obvious that the 3 down is going to combine to be a velocity of, so we're going to say, oops, that was supposed to be green. We're going to say a velocity of the plus 3 up, right? So velocity of the Boat relative to the shore is going to equal, this is review of yesterday's stuff, right? Is going to equal the velocity of the boat relative to the water plus the velocity of the water relative to the shore. And so when we add those up, we're really getting a +6 and a -3 adding, giving us that 3 that just makes sense looking at things. Okay, so that's what this was here as well, velocity of the boat relative to the shore. I'm glad I decided to show this extra because it wasn't shown as well here. So this one is also, of course, velocity of the boat relative to the water plus the velocity of the water relative to the shore. Oof. Smart words. You don't see it on your end because it's just whatever, but I don't know if you hear the typing or writing or not, but it's delayed. All right. I'm just going to hit save because sometimes when things are delayed like that, it's signs of bad things to come. So now, what about aiming? What way do we aim to go straight across? Okay. So when aiming straight across, we know we get swept 26.5 degrees downstream. And so which way should we aim to go straight across? Okay. So hopefully you have an answer that you thought of yesterday about this. And, you know, I wouldn't be surprised if a lot of the answers are this, that you aim upstream at 26.5 to counterbalance the 26.5 downstream, and you'd go straight across. Unfortunately, sometimes things are complicated. And so even though that's a very logical guess, it is not true. And I'll try to justify why. One way to justify why is that when you're heading upstream, your velocities are subtracting. When you're heading downstream, your velocities are adding, right? And so if you're aiming straight across, really you're just adding velocities. As soon as you start to aim upstream, you're subtracting velocities. And so it's not the same effect, right? So that's just an intuitive way to think about it. And so basically you can tell then that, I'm trying to think of this here. Would you have to aim at a bigger angle to compensate for that? I'm having trouble thinking through the logic of it on the fly here. Okay. So let's do the math of this. The math version of this is that we have this situation as our triangle if we're thinking it's 26.5 degrees, right? Whereas this is the triangle that we know the physics is true for. You notice the difference between these two triangles? Like there's a problem in the difference between these two triangles. The geometry is not the same. In this triangle, that is the situation we're actually dealing with, the longest side isn't the 6, you know? And in this case, the longest side is the 6. So you can tell the geometry is just not going to be true, right? If you put 6 and 3 together and you get 26.5, well, 6 and 3 together this way is not going to be 26.5, right? And so what you have the 6 now is your longest side and so on, right? So what we're going to do is we're going to say, okay, this is what we want. We just know that's not the angle. We want theta. So we're going to say, okay, well, what ratio are we talking about? It's going to be opposite over hypotenuse, right? So we're going to have sine of theta equals the 3/6. So sine of theta is the sine inverse theta is the sine inverse of 3/6, which is going to be 30 degrees. So I was going to say it earlier, but it just was too much of a chicken, I guess. But you have to aim a little further upstream to compensate for the fact that you're going slower and you're trying to fight the current and so on. So you have to aim a little further up. You could say this as part of this description. You have to aim further to compensate for the fighting the current and so on. This is nice because it gives you the exact angle. Okay, so understanding how this stuff works is powerful. You can predict and answer and explain anything to do with it, right? So that's the river question done. All of those challenge questions answered, taken up, justified, fully explained, as best I can, at least right now. And yeah, so the next question that we'll tackle, just as a tiny bit of new stuff here that's to do with this concept, right, is just, calculating things like this, right? If a plane's flying at 220 meters per second in wind that's blowing at 50 meters per second east, if the plane wants to go 100 kilometers north, what direction should the plane, does the pilot need to aim the plane so that the wind sweeps the plane to the north direction they want. This is actual aviation calculations, right? Airplanes and pilots and air traffic controllers and whatnot. They calculate this because then they fly kind of directly to where they want rather than having to keep correcting and whatnot. It'd be incredibly inefficient, waste a lot of fuel and a lot of time and so on. So what direction does the plane need to aim? And what's the resulting velocity of the plane relative to the ground? And how long does it take to get there? These are all things that we're equipped to be able to answer. Okay, so let's think about the vector of the plane and the vector of the wind, right? Let's have a 200 of the plane, right? So let's call that the 200 of the plane. Let's just group those together so it'll stay as a 100 meters per second, right? So there's the plane. And let's have a 50. So a 50 east. Now this one has a direction to do with it. So, but that's about, right? 50, 100, about like that. Okay, so there's the 50. Not that it matters if it's to scale, but I mean, reasonable, right? So we have these two vectors that we're thinking of as these directions. Now the plane's obviously not going to fly that way, and it's not going to fly east, obviously, in order to try and go north, because it would be going 250 meters per second east, never getting north, right? But I have them made and ready to use, and so what we're going to do is we're going to get new copies of each of those, bring them down here, and say, okay, well, we want to end up directly north, right? So if I'm starting somewhere, let's just put a little starting point, right? I want to end up directly north. So obviously if I aim straight up, obviously it's going to sweep me east, right? My goodness, this thing's so slow right now, right? It's going to sweep me east, so I'm not going north. And so obviously I'm going to have to aim a little bit this way in order to get the wind to sweep me towards directly north, right? And so if I put a line in here, it changes to be a dotted line in a second, but there's my directly north line. You can tell my angle was pretty close, but I'm swept a little bit too far, right? So what we can do is you just get this tweak this a little bit. I know people these days use tweak a little differently. All right, but that changes by the week, so I don't need to worry about that. All right. Are you tweaking right now? Yeah, OMG, right? All right. Computer is driving me a little bit crazy. Its slowness to respond. We have that as our situation, right? If you line it up like that, everything's gonna work. And all we're wanting to know really is what angle we need to be at, right? So if I get my meters per second out of the way here now that things are rotated, I can put a label in here and say, hey, what angle is this at? And then that's what the air traffic controller tells the pilot to, what kind of heading to take, right? So a little bit, if it was one of the silly multiple choice questions, it'd be like a little bit west, whatever would be an answer to that, right? To figure out the actual direction, obviously we've got a nice right triangle situation going on here. And so you can see that relative to the theta, we've got the opposite side and the hypotenuse. And so it shouldn't be any surprise that we're going to say, okay, sine of the theta angle equals opposite over hypotenuse. And so we've got sine of theta equals 50 over 200. And so we take sine inverse of both sides. And we end up with the angle that we want. Right, sine inverse of that gives us 13 degrees. So already we have the answer for which way to aim. So it seems like a more complicated question maybe than it really is. Hope you can see that now looking at it. Right? What is the resulting velocity of the plane? What's the velocity of the plane relative to the ground. So that's where we can just calculate, obviously, that value, right? So we have the plane relative to the ground. We're looking for this velocity right here, right? Velocity of the plane relative to the ground in part B. And so really it's just a Pythagorean theorem question, right? So I think we can just say, okay, well, Pythagorean theorem is this. Oops. As I put the plus on the other side, so I botched it a little bit. But so the hypotenuse is the one that's by itself. So we've got our 200 squared equals a 50 squared, and the velocity we're looking for squared, right? So velocity squared plus the 50 squared. And so the velocity squared we're looking for is the 200 squared minus the 500 squared, or 550 squared, sorry. And so velocity squared equals, well, let's just say velocity squared equals whatever number, and the velocity ends up being, I'm sure you can calculate this yourself here, 214.3 meters per second. Okay, so velocity of the plane relative to the ground ends up being that, which of course we've set this all up to be north, right? So this many meters per second north. And then if we want to have that final answer of how long it takes, well, we know we're trying to travel 100 kilometers or longer, given that it's an airplane situation. But the question is what it was written as, so let's just do it. Final answer bit here is just part C, of course. And so we have C, and we have velocity equals displacement over time. And I'm putting the direction in the north velocity in with the north direction and so on, right? So 214.3, sorry. And the displacement is 100, and we're looking for the time. So we can solve that out easily enough. I'll show some steps this time. I've been skipping a couple times here, but right. So multiplying both sides by delta t, get rid of that, and it leaves us with 214.3 delta t equals 100. And then we just divide both sides by 214.3. And we get delta t equals, and it gives us 466.6 seconds and so on, which you could convert by dividing by 60 if you wanted, or how many minutes this is and so on. So like I said, obviously it's this isn't, maybe it isn't the whole journey, right? This is like 7 or 8 minutes, whatever it is. Yeah, 7.8 minutes, which you could convert to minutes and seconds if you wanted to and so on, but just not really relevant at this point. Okay, so that is the fairly straightforward version of this kind of thing, even though it seems kind of challenging at first, right? The idea of what way you aim, but you just make the drawing be what you want, right? Make it so that the blue vector in this case, the 220 or 220. Oh my gosh, I can't say words right here. 200 and the 50 are adding to go perfectly straight up, right? So that's all done. The math for the previous one just required SOHCAHTOA because it was a right triangle situation. If the wind wasn't directly east, right, this is because, right, since the wind was east, but clearly the wind is not always east, and so that'd be a pretty limited skill set if you're applying to be a air traffic controller, and you'd probably need to be able to do some other calculations, right? So let's see what this would look like, right? What if the wind wasn't directly east? So, or if the plane didn't need to go directly north or whatever, right? The triangle would not be a 90-degree triangle, and so sine or cosine law would need to kick in. That's why the warm-up question earlier, get you ready for this, right? So draw the triangle for if the wind was blowing at 50 east, 30 degrees north. Let's grab our vectors. Let me just grab that whole. Let's do that. This, and this. Copy and paste here. Right? And so now we're going to have the wind going east 30 degrees north, first of all. So if it'll let me change the angle of that, east 30 degrees north. And the so we got that. I might make these bigger too, just to make it easier to follow here. But the way it stands right now wouldn't be directly north because we were at an angle to end up directly north already, right? So if you look, this ends up being like a little bit this way right now, right? So we're going to have to aim a little bit less of an angle. So this one here, we're going to have to rotate, ungroup here. Just have to regroup this so that I don't change the length by accident. But yeah, like a little bit like that maybe or something. It'd be hard to get this exactly right, but you get the idea. Right? So one adjustment here, we'll go with it. Okay? So that right there is now our going north. The bells. So that's our heading directly north, and now we're tasked with trying to figure out what angle we need to be at now. Right, so now this is a different angle. You can tell this angle in here is now smaller, right? Theta is going to be smaller than before. Right, because the wind isn't sweeping you east as much, so you don't need to aim west as much. Just logical stuff, right? And so when we try to work this through, let's think about what we do have. We do have the 30-degree. What else do we have? Based on that being 30, we have a 90 here, and then that pins this top angle as 60, which I think is a pretty big milestone to try and figure things out, because that's actually one of the angles of the big triangle. And so if you look, what you have now, you have an angle, the 60 and the 200, right? And then you have the 50 and the theta. So the way I show sine law is absolutely that. If you have a crisscross of information, you have enough to use sine law. Okay. So if you have a crisscross of information, you can set it all up and just get it. So whatever you're looking for, you just start with. And so we're looking for theta in this case. So let's start with sine of theta and fill in the sine law around it. So sine of theta over the opposite side, so over the 50, is equal to the sine of the 60 over the 200. I almost think maybe it was 220 at some point, because I had numbers like that. Was it 220? It was 220, but I did everything as 200. So let's just change that to 200 and be done with it. So, oh no, that means that my calculations weren't right though, because I had the calculations worked out. Okay, better change then. Sorry, 220, 220. These numbers are all correct for 220. So I'll just modify that. So if you were running the numbers, my 200 number wouldn't work. Wouldn't give those results. So let's change that. Everything else is good. I just have to get rid of one of those zeros and those zeros. This just needs to be 220. And then I'll have all my stuff right from the start. I said 220 at one point, and then, yeah. All right, there we go. So those numbers actually work. The 220 is the actual speed that everything's based on. So again, here, change this guy to be 220, and this one to be 220. There we go. Oof. 220 for it. All right, here we go. So yeah, we're just multiplying both sides by 50 and evaluating, right? So it's not actually too bad. But just the idea of, setting up the triangle seemed intimidating maybe. But sine of theta equals sine 60 times 50 divided by 220, and so you end up with whatever that is. So that ends up being 0.1968. Other decimals maybe if you want. And of course, then sine inverse. Gives you the angle. And so we end up with theta equals 11.35. So a little bit less as expected, right? Check. An angle of 11.35, so you're going to say like, therefore the angle, whatever would be, right? You'd say north 11.35 degrees west would be the direction you need to aim. And that works, I think, right? Another way to think about this one is I want to just show it to you in the end here. I'm just going to delete this one because it's sloppy. So delete that page. Another way to think about this one's kind of neat is that if you look at the diagram we had, it's another driving principle or way of thinking about it and getting a solution. So let's look at our diagram. I'll just clean up some of the stuff that we don't need here. Go. If you look at what the component of this velocity is, so if you look at the Vx, component here, so Vx of the 220, and you look at the Vx of the wind, right? Vx. I don't know what you want to, I guess because it's color coded, it's fine, right? But basically those just have to match. And so you could actually just literally set the X components to cancel out in order to end up going directly north. Of course, this is, only in a case where you're trying to end up directly north, but it's a pretty slick way of going about it as well. Right? It doesn't involve sine law, right? If you didn't know sine law or cosine law, you'd still be able to get this question, as long as you know how to do components with just basic sine or cos. And it's kind of neat that it works. So I thought I'd show it. All right. So there you go. That is it. I'll put some questions there for you. Got a sneeze coming, so I better just sign off. Yeah. Thank you very much for watching. I'll talk to you later.